Well, H2, hello again. Now that we have a clearer understanding of what hydrogen is, let's analyze why hydrogen is important now. In this chapter, titled H2 Today, hydrogen is not something futuristic. We will see where we stand and why suddenly hydrogen seems novel, when I can already tell you that we have been using it for hundreds of years. Let's begin. Ayusin, un tetero. Okay, let's start from the beginning. As you already know, the society we are in is experiencing a period of energy transition to curb the environmental problems caused by fossil fuels. Already in 1997, the first climate commitments were agreed upon in the Kyoto Protocol, but in the Paris Agreement of 2015, clear targets were set to curb global warming. In summary, the planet as a whole must be neutral in greenhouse gas emissions by the year 2050. As a result of this, more than 70 countries have made public their strategies to achieve net zero CO2 emissions. Some social events, like the recent war in Ukraine, have accelerated the search for energy sovereignty, and the European Union, with the Repower EU Pact, is betting on increasing energy efficiency and massive electrification. The topic was opened. Electrification? Is it an enemy of hydrogen? The answer is clearly no. Both electrification and hydrogen are alternatives to decarbonize the energy market, which is immense. There are certain fields where electrification cannot occur, and that is where hydrogen finds its opportunity. These sectors are called hard to abate and are as follows. The first of them is the chemical industry. Hydrogen is an atom necessary as such in products like fertilizers or methanol, which contain H as in NH3 and CH3 or H. Here, there is no competition with electrification, and hydrogen has been used for hundreds of years. The second sector is steel production, where hydrogen is used to reduce iron oxide. Although heat can be generated through electrification, there are applications that require high temperatures that can only be achieved with hydrogen combustion. Moreover, although electrification is indeed useful in transportation, hydrogen offers many more advantages as a fuel for heavy and long-distance transport, as well as for large-scale energy storage. Now, the point is that hydrogen has been used in the industry for a lifetime. The problem is that this hydrogen was what is called gray hydrogen, meaning it comes from fossil sources. If we want to decarbonize energy, we need to obtain hydrogen from renewable energy sources to be able to say it is clean hydrogen. And to understand that, I present to you the famous hydrogen value chain. The thing is, the world of hydrogen has its intricacies, but we can mainly divide it into three parts: production, storage, and transport, and end uses. The first thing is to produce the hydrogen. As we have already mentioned, we do not find hydrogen in nature in the form of gaseous H2 in the quantities we would like, so we have to produce it. And to make it renewable hydrogen, we need renewable energy sources, such as solar or wind. Additionally, we need water, H2O, since that is where we will extract the hydrogen from. With water and electricity, electrolysis will be carried out to convert H2O into H2 and O2, gaseous hydrogen and oxygen. Everyone must be very clear that renewable electricity is needed to produce green hydrogen. That is why all photovoltaic, wind, etc. are so closely linked to the field of hydrogen. If we do not have renewable production, we do not have hydrogen. Well, the electrolysis reaction shown occurs in a device called an electrolyzer. We will see later all the types of electrolyzers that exist. If, on the other hand, hydrogen is produced using carbon-based fuels, it is not renewable and emits carbon dioxide. That hydrogen is called gray hydrogen. Perfect. So once we have our gaseous hydrogen, we have two options: transport it to its place of use or store it. If we add gaseous nitrogen, we can produce ammonia through the Haber-Bosch process. This ammonia can be transported much more easily and used in various applications that we will see later. If we combine the hydrogen produced with carbon dioxide, as synthetic gas and water vapor can be generated. This methane, CH4, also has many applications and is crucial in heating and in industry to produce light and heat. But hydrogen combined with CO2 can also generate synthetic liquid fuels like diesel, gasoline, kerosene, or methanol. Here you have the reaction for the latter. As you can see, we can transform hydrogen into many other energy carriers, but we can also leave it as it is, store it in tanks in gaseous form, transport it through pipelines called hydroducts, or even liquefy it, cooling it to minus 253 degrees Celsius to obtain liquid hydrogen with a smaller volume of occupation. Very well. All these obtained products make hydrogen have a lot of end uses such as mobility, the chemical industry, the steel industry, fertilizers, and plastics. But I won't dwell much more here as there is a whole chapter dedicated to hydrogen applications. Great. You already have in mind the key outline of the entire general overview related to hydrogen. And as you can imagine, this needs to be regulated. I am not going to go into all the existing regulations, but I would like to mention some requirements related to hydrogen. At the European level, the Renewable Energy Directive proposes hydrogen as an RFNBO, renewable fuel of non-biological origin, but to be considered a renewable fuel, as it must meet a series of requirements specified in the delegated acts. The first delegated act, for example, establishes 3 criteria. The first is additionality. The electricity used to produce hydrogen must come from renewable sources that are additional to those already existing. In other words, we cannot start using the wind or solar energy we already have to produce hydrogen. We need to generate more new energy. The second criterion is geographical correlation. This principle states that hydrogen production must be located in the same region as the renewable energy generation used. They have to be close. The idea is to avoid losing energy in transmission and to favor local solutions. And the third criterion is temporal correlation. The renewable electricity used to produce hydrogen must be generated more or less at the same time as the hydrogen, simultaneously. Until 2030, the correlation is monthly, but from then on, the aim is for the correlation to be hourly. The second delegated act, on the other hand, seeks to quantify the greenhouse gas emissions of these new renewable fuels. Alright, so far we have talked about European regulation, but let's focus a bit more on Spain, whose strategy is of course aligned with Europe's. Spain has the long-term decarbonization strategy for 2050 to achieve a climate-neutral economy. Additionally, as a strategic plan for the 2030 horizon, it created the PNIEC, or National Integrated Energy and Climate Plan, and a renewable hydrogen roadmap, which aims to achieve a series of objectives. By the year 2030, Spain must have an installed capacity of electrolyzers of 4 gigawatts. 25% of hydrogen consumption will be in industry. At least 100 public hydrogen stations must be built to enable the operation of at least 150 hydrogen buses. We must ensure that at least 5,000 heavy transport vehicles and 2 train lines are hydrogen powered. And for this, 8,900,000,000 euros must be invested. With all this, carbon dioxide emissions must be reduced by 4.6 million tons. There is still much to do, right? What is clear is that we are on the path, and although the hydrogen race is a long-distance race, it is a reality today. For now, watching this course is already a sign that you are willing to contribute to it, so I'm going to give you a little break before starting the next chapter. See you!